a little bit faster in that regard. And it peaks out around 110 or so megabytes a second. This particular graph shows the same situation where we have one process performing I/O. It's actually a 256 megabyte file, and it's only written on one OST. So we're not striping across multiple OSTs in this, we're just on one OST. And we saw before where we had an increase in performance with the larger stripe sizes. So in this particular, the results of this are trying to investigate the interaction between the stripe size and how much data I'm actually writing. So we have a couple of graphs here. So there's a red bar, which is actually red bar, a blue bar, and a green bar. So the red bar is actually, in this particular test, the application is writing 32 megabyte chunks of data. The blue bar, it's writing 8 megabyte chunks of data, and the green bar, it's writing 1 megabyte chunks of data. So the chunks of data that are being written in each operation is getting smaller. And along the bottom is the stripe size, so it goes from 1 megabyte to 128 megabytes. So you see that the green bar is flat all the way across. And of course, that's the 1 megabyte transfer size, and the stripe sizes are either equal to it or larger than it. So we either have multiple transfers going into a single stripe or one transfer per stripe. So the performance of that particular case is limited by the chunks that the application is writing. So it's writing these 1 megabyte chunks of data. So that's where it's limited. You get increases in performance if you increase that to 8 megabytes, but it's still low on the front end. So at the front end of this, it's limited by the stripe size. So this 8 megabyte sort of write operation is being chunked up into 1 megabyte chunks or 2 megabyte chunks. The performance steadily increases as you increase the stripe size, and the increase is a little bit past 8 megabytes, so about 16 or 32 is the actual max of that one. And the same thing happens with the 32 megabyte transfer size. That's the best performing case, although it still performs rather horribly with a 1 megabyte stripe size, but increases rapidly as you increase the stripe size. So performance can be limited by the amount of data you're writing at one time in the application, and also can be limited on the file side, on the file system side of things, where you take your transfer and chop it up into little smaller bits, or just aggregate them all. So single shared files. So as I mentioned previously, using a shared file, the layout of the data in the file is very, very important with performance, and I'm going to show you that real quick. So I'm going to show you two shared file layouts. So this is one of them. And this is a fairly common one where, in this particular example, we have a file in which 32 processes are writing data to it, and each process is writing 32 megabytes worth of data, although their data resides in contiguous chunks in the file. So you see in this pictorial where process 1's data comes before process 2's data comes before process 3's data, and so on. We can have another file layout, which is also fairly common, except for each process. So this file is the same size, still 32 processes writing data. However, each of those 32 megabyte chunks is being split up into 1 megabyte components, where each process writes its first 1 megabyte, then each process writes its second megabyte, all the way up to 32. So this is sort of a strided access pattern, where each process is actually writing its data strided throughout the file. So this pictorial, I need to describe this a little quick. We have another bar graph. 32 processes are writing data. This single file is striped over 32 OSTs. So one OST per process. And the difference between the bars is we have a red bar, blue bar, and a green bar. The red bar uses a 1 megabyte stripe size, file layout number 1, the first one I showed. The blue bar uses the 32 megabyte stripe size, and it also is using the first file layout. So the difference in performance is major in this. And the reason is that, as you remember in the first shared file layout, each process wrote 32 megabytes in a contiguous chunk in the file. So the first process has its 32 megabytes in the first part of the file. The second process has its 32 megabytes right after that, and so on. If you use a 1 megabyte stripe size, that 32 megabyte block is chopped up into 1 megabyte bits and spread out across all 32 OSTs. And that happens for every process. So every process is talking to every OST. So the way we were thinking about this before is each OST now has 32 processes talking to it at once. So there's lots of contention there. In the second case, using a 32 megabyte stripe size, each process's data is on a single stripe on a different OST. So they're actually separated. So that increased the performance to now 1.8 or so gigabytes a second. The green bar is lower than the rest, and this is shared layout number 2. So in this layout, as I showed you before, those 32 megabytes for each process is strided throughout the file, where in 1 megabyte chunks. So if you used a 1 megabyte stripe size, then all of the stripes from each process would land on the same OST, although split up. It won't be one operation, it would be 32 1 megabyte writes. The reason why it's lower performing is because it's strided. So it's not contiguous in the file, so each process has to write to different portions of the file, so that decreases the performance, although it's a lot better performing than the first case. As far as a file per process is concerned, so the thing you have to worry about is scalability with the number of processes and the number of files that you're writing. So as we demonstrated before, a single process doing I/O needs to communicate with at least one OST, or just one OST. It shouldn't communicate with 2, 3, or 5 at the same time. So in this particular example, each process is writing a 128 megabyte file, and it's writing in 32 megabyte chunks. The red bar is using a 1 megabyte stripe size. So it's generally the lower performing of the cases, but it's the most scalable in this particular sense, mainly because it doesn't fill up its bandwidth that quickly. But the problem with the file per process is as you increase to, say, 5, 6, 7, 8,000 processes or files, you start getting contention for file system resources. You get metadata contention for having to open all these files at the same time. So you get a little decrease in performance at the end. Using a 32 megabyte stripe size, the peak comes sooner. That's because you're filling up your bandwidth a lot quicker. So it's, but it still has the same overall sense where the low number of processes or files, lower performing, you increase performance as you fill up the bandwidth, and then as the processes conflict with one another or battle over the same file system resources, you get a decrease in performance. Okay. So now I'm going to talk about MPIO real quick. So the way I discuss this is in terms of I/O libraries. So a lot of people use I/O libraries to perform their I/O, such as HDF5 or NetCDF, and those are built on top of MPIO. So such libraries are abstractions off of MPIO. So MPIO will allow you, if you give it enough information, to increase the performance of your I/O. So the goal of this is to understand how information flows into the library and how you as a user can supply that. In terms of these other libraries such as HDF5 or NetCDF, you don't have to supply it. Those abstractions apply the information. But to help give you a sort of a consideration of what goes into it, we'll go just into MPIO directly. So the first thing, of course, is opening a file. So a lot of these slides, I use only the C syntax. So there's a note for Fortran. So the only difference between the C command lines, between the C and the Fortran command lines, are in Fortran they're actually subroutines and not functions. So you call. In Fortran there's an extra argument. It's an integer at the end. It's called IError in order to get the error code. And all the C data types such as MPI-COM, MPI-info, and MPI-file, all those are integers in Fortran. So I won't discuss the differences anymore because that's all there are. The call looks exactly the same. It's not case sensitive like it is in C. So to open a file, you can open a file per process, or you can open a shared file, and that's controlled by the communicator. So if you use MPI-COM world, for instance, you're opening one file shared between all the processes or all the members of that MPI communicator. If you use MPI-COM self, you open a file per process. And other data you sort of put into this, you can put in the access mode, whether it's write-only or read-only. Also, you can put in MPIO hints into the MPI info section in order to give MPIO some more information. I'll talk about that almost near the end of the talk, or near the end of this section. So once you have the file opened, whether it's a file per process, oh wow, there we go. Whether it's a file per process or whether it's a single shared file, you need to set up a view. Now, you don't necessarily have to set up a view. The default view of the file is that every process can access every bit in the file. Now, by defining a file view, what you do is you're telling MPIO in particular what data in the file can this process access or change or read or write. So the way that's done is usually with derived data types. So as far as the arguments are concerned there, you give it a file handle described by the open command. You set an offset, so this file view can start anywhere in the file, whether at the front of it or down in there. The MPI data type E type is actually the elementary data type. So this is the data type that sort of it defines the units of the file access. So if it's a double, it's 8 bytes long, and if it's an integer, it's 4 bytes, and so on. Now, the MPI data type file type actually controls what portions of the file you can look at. The process can either read or write only these portions. I'll have to go into more detail on that in a second. So as far as MPI derived data types are actually made up of smaller bits. So they're made up of elementary data types such as MPI double or MPI integer. So MPI double is actually a C MPI data type, and MPI integer is actually a Fortran one, but you get the point. Derived data types can contain holes. So you can have a derived data type which has a total extent, but within it is holes. So you can actually only access portions of the data type. And I'll go into more information about what that entails. So derived data types pass information to MPIO. So it's a fairly powerful way to do this, where you actually telling MPIO, out of, say, this set of 20 bytes, I can access this set of 6 bytes or this set of 4 bytes, and not any of the others. So we're going to talk about the subarray data type. So let's assume we have a program in which we need to store a 2D array. So it looks like a matrix. In this particular example, it's an 18 by 18 array. So those elements can be anything you want. They could be doubles, they could be integers, they could be characters. It really doesn't matter for this discussion what the elementary data type is. It just matters how many of them there are. So in this particular case, we have a global 2D array which is 18 by 18, and we say we want to split this among 9 processes. So 9 processes have a block, and that's where the dotted lines come in. So they have a sub-block. They have a subarray, a 6 by 6 subarray. Now the things you need to know in order to reconstruct this global data structure from the individuals is you need to know how many individuals there are, so there's 9 here, the size of the subarray, the size of the global array, and also where each of the subarrays fit into the global scheme, so you need an index. So you see the red area there, that's sort of the first, so one of the processes has that data, and that's the one we're going to focus on. So this is a parallel program, so each process calls MPI set view, and it can set its view different than the other one, so they're not trying to write or read to the same portions of the file. So one of the processes we're concerned with is the red section, and it has an index 06. So it's in the sort of 0th row is where it starts in 6th column. So the extent of this whole data type is 324 elements, so it's 18 by 18. So we define this data type in which it depends on what your formatting is. So in Fortran, you usually use to column major, so you run down sort of the columns first, or in C, it's row major. So depending on how this 2D array is linearized, you get a different sense for what the data type looks like. So in this particular case, the red area is what you want, so you end up with this linearized portion where if it's column major, you have those first 6 columns blank. So those are blanks. The reds are actually spots, so you have 6 elements, which is the column, and then you have another set of 12 blanks, 6, so forth and so on. In row major, so it does matter what your ordering is because it changes what the data type looks like. You have a different number of blanks in the front and the back, but the middle part is about the same, so it's either for each column or each row. And the reason why they're the same is because this is square. But